Hello, this is Group J's Task 9. For this week, we have several changes from last week's task. Last week, we had a circular beam, which was supposed to be the wing of a plane, and this week we will model a real kind of wing using a template with Excel for an airfoil. First of all, I will talk about the equations needed to compute the values of the deflections, which we will use later in the 3D beam program. These equations can be seen here and relate each displacement in each direction with the one which we will use later. As we can see here, this would be in the x, in the y, and the z direction. Here we will relate the deflections with the forces and the moments. That's it here. So, first of all, as always, we will define our material. We will use this material named T300EP. These values were given, and they're supposed to be similar to the ones used in real life models. We also have these laminates. We will use 4 different laminates: leading, spark up, trailing, and web. We assign the thickness of each part and each angle and the material which they will all use, which will be the same, T300EP. Once we have established the laminates, we can establish the section. We compute a section for an airfoil, and this time it will be more complex than last time. We will have a section which looks like this. The most important part will be determining the NACA number. Each of these numbers defines the geometry of the section: the chord line, the timber line, and the thickness. In our case, we will use 2 for each 2 for M, 2 for P, and 22 for T, getting a NACA number of 2222. We can show that this value was employed here. In option 1, we select airfoil. In key point number, we select the center for the section, which will be 1000. Then we use the NACA number and the X point where the axis will start. The chord will be the total length, and the laminate number, the laminate we're going to use: 1 for the top, 2 for the bottom. Here we are defining each of the sections. Because it's divided by a shear web in the middle, here we see that they go from each point. And in point 9, we are defining the web point. The web point is different to the other ones. We establish here the percentage where it will occur through the section, being in the middle of the section. This will provide us a section which will look like this. This will be our shear, and this will be the section with NACA 2222. There's an important part which we have to comment. As we can see here, the thickness of the airfoil throughout the whole geometry is the same. This is not what happens in real life, where the thickness of the wing is much thicker beside the airplane and gets thinner and thinner as it goes along. In this geometry, we can see how we apply the reduction. This reduction is stated in the part of Y scale and Z scale. If there was no reduction, this would be a 1, and because there is a reduction, it will be 0.5 and 0.2. I forgot to mention that for each sector, we will select the laminate we will use. I want to show which part will be selected for each. One second. Yeah. If this is our section, or one kind of section, our shear web would be in the middle. This would be the first section, second section, and so on. Once we have defined the section, we can return and select the geometry. For our geometry, we chose a length of 30 meters and we divided it into 20 nodes. After that, we will select the loads applied. These loads try to imitate real life behavior. In our case, we are applying the forces exerted by the weight of the air wing when the plane is not flying. This is a force in the Z direction, which we computed as these values. It will be applied on each point, of course. Once we have the loads, we calculate the values and we obtain the following. So this will be our deflection. As we can see, it's in the Z direction, as the force is applied in the Z direction. So this part of the problem consists in comparing the two results, the one obtained by Excel with our Excel calculations using the equations that we saw before in the slideshow, in the slides, which were these ones. So we will compute it the old way, and then we use 3D beam and compare the results. Here we have some pictures with the results. This is the deflection, and this, as we showed before, is the section. The results, the numerical results for obtained with the 3D beam program can be shown here, being U3 displays the deflection in the Z direction. As we can see, the displacement in the Z direction is much bigger than in the Y and X direction. This makes sense as the force is applied only in the Z direction. Here we have important values of 4.5 to multiplied by 10, and here we can see that it's just millimeters. These are the results which we obtained with the Excel, being the deflection minus 5.6 meters, which compared to these values are in the same proportion, but they're quite different. Because here we have 45 meters. This can be explained as the 3D beam being a much more precise way to calculate these deflections, as it has a better defined section than what we use to calculate the values with the Excel. So this will be all for task 9.